Okay, so the last SL technique to know about for topic 11 is NMR spectroscopy, or proton nuclear magnetic resonance. Um, Actually explaining how it works is really not going to be required. There are just a couple of things to be aware of in terms of how the HNMR operates and what type of electromagnetic radiation it uses, but mostly what the topic focuses on is using the data from an HNMR readout to help you figure out things about a molecule's structure. So how does it work? It's based on that if you have a nucleus with an odd number of protons and neutrons, and so the example that we're always going to use is hydrogen, which has one proton only, so it has this odd number of particles in the nucleus. If you have a nucleus like that, then that nucleus acts like a very tiny magnet because nuclei are spinning in a similar way to the idea that electrons are spinning. So the way that this machine works is it puts a substance under a very powerful magnet, an external magnetic field, and when it does that, it's going to make these little nuclei line up with the magnetic field or against the magnetic field. So that's a concept from physics that you may have covered in the past, but magnetic fields have north and south poles, and so you can either align with magnetic fields in the same direction or you can go against them, but you're not going to be anywhere in between. So those two different ways that the nuclei can align have slightly different energy states. And so as the magnet is turned on and off, and the nuclei are lining up in these two different states, the difference in energy causes, as the magnet gets turned off, a little bit of energy gets released from the nucleus. It's a very tiny amount of energy, the difference between these two states, and it happens to be in the radio wave region of the spectrum. So if you're going to remember anything about HNMR and how it operates, it's based on using the hydrogen 1 isotope because it has an odd number of nucleons, protons in the nucleus. The type of radiation that it's going to rely on are radio waves, and it uses this external magnet, causes the nucleus to flip back and forth between these different energy states, and radio waves end up getting emitted. Okay, the exact type of radio wave that gets emitted depends on the type of chemical environment that the hydrogen is in. And so even the difference between a hydrogen that's on, let's say, a CH3 methyl group and a hydrogen that is on a CH2 group in the middle of a carbon chain, those hydrogens will actually emit slightly different types of radio waves, slightly different energy radio waves. And so what this device is going to let us do is it's going to let us pick out the number of different chemical environments of hydrogen in a molecule, and it's going to let us see the relative number of hydrogen in each of those environments. And this will be a lot easier to understand once we look at some examples on the following pages. One more thing about how this machine operates. It's always important to have a reference standard by which you compare your data to. And so the standard that gets used for the HNMR, which you should know by name, is called Tetramethylsilane, or TMS. And I'll show it to you on the next page so you can have a sense of what it is. It's down at the bottom. This is tetramethylsilane. It has a silicon atom at the center and then 4 methyl groups off of it. So that kind of makes sense why its name is tetramethyl, meaning 4 methyl groups, silane meaning silicon. So it's a silicon with these 4 methyl groups off of it. It's a good standard because this technique generally is used on organic molecules, and organic molecules never contain silicon. Therefore, the type of radio waves that are going to be emitted by this molecule are very different than the ones being emitted by organic compounds. So it avoids confusion with hydrogen atoms in the sample that you're testing. It also has a lot of hydrogens on it. It has 12 hydrogens all in the same environment, and therefore it produces a very strong signal. It's very easy to pick up with the device. And so it ends up being a good standard for those two reasons. It gives you a clear signal that's very different from the sample being tested. And so the signal that gets produced by this molecule is said to have a chemical shift of 0. And so we'll see in the readouts that the x-axis is referred to as the chemical shift. And so this is just the standard, the 0 value is based on this TMS molecule. Okay, so in terms of actually figuring out the different number of hydrogen environments, it's important to draw out structural formulas. So for ethane and propane, let's do a little pause for a second. So if we look at these three molecules, ethane, propane, and methanol, we're going to identify first the number of different chemical environments of hydrogen. It sounds very fancy, but it just means you think about the hydrogens, what it's like, what everything is like around this hydrogen, and try to figure out how many different types of places are there for hydrogen to exist in this molecule. I don't know if that was any clearer than the number of chemical environments of hydrogen. So let's just look at examples to understand this. So in ethane, you've got these three hydrogens that are clearly all in the same environment. They are all connected to this same carbon. So the hydrogens that are connected to the same atom always exist in the same chemical environment. So these H's are on a CH3 group that is next to a CH3 group. Well, if you think about these three hydrogens over here that we know are going to be in the same environment, they are on a CH3 group that is next to a CH3 group. So actually, both of these sets of hydrogens are identical to one another. So there's only one environment in this first molecule. All 6 of these hydrogens really have the same existence. They are attached to a carbon that is attached to a CH3. That's true for all 6 hydrogens. In the next one, I've definitely got an environment here because they're all attached to the same carbon atom. But I would say that these 3 hydrogens have the exact same environment. If you look at both of them, you've got H's attached to a carbon that's attached to a CH2 group, right? H's attached to a carbon that's attached to a CH2 group. So these 6 hydrogens here form one environment that's the same. And then these two have a slightly different environment. These 2 hydrogens are on a CH2 group that's next to or in between 2 methyl groups. So that's a second hydrogen environment. So there are 2 different chemical environments in propane. As we look at methanol, these 3 are in the same environment because they're on the same atom. And that's clearly different than this H, which is on an oxygen. So there are 2 environments here. The second important thing for an HNMR is how many hydrogens are there in each environment relative to one another. So in the first one, this doesn't really matter because there's only one environment, so we don't really worry about that. But in this one, there are 6 hydrogens in one environment, and there are 2 hydrogens in the next environment. So what you would end up seeing on the HNMR spectrum is that the peak for the first environment is going to be 3 times as high as the peak for this environment, for the CH2 group, because there are 3 times as many hydrogens in this environment as there are in this environment. So the ratio, really it's the areas underneath the peaks, but usually it shows up as like the height of the peak. One peak should be 3 times as high as the other peak. And if we look at this one, we again get a 3-to-1 ratio. And so that should be sort of the relative heights, relative areas of the 2 different peaks. And then the third thing to think about is called the chemical shift, which is how far down the x-axis these things show up. The chemical shift values are listed in the data booklet, and we'll look at that next. The further left these peaks are, the higher the chemical shift. So it's a little bit odd the way it's listed. The reference value, that TMS that we talked about, will be down here at 0. And so here is table 27, HNMR data. It tells you it's relative to TMS. And so if we were looking here and wanted to try to predict their chemical shifts, well, this tells us that H's that are on methyl groups should show up around 0.9 to 1 on the x-axis, whereas H's that are on a CH2 group in the middle of a carbon chain should show up slightly farther down, and ones that are on alcohols down here should show up